Hi, and welcome back to another edition of Easy Theory. And you read the title right, so hopefully that this is going live. Because what I'm going to do is I'm going to record this um, instead of recording this. I'm going to have it go live instead, so that in case that something wrong goes in the middle, then I don't have to restart everything. So let's just make sure it's going live. And yes, it is. So let's actually get started. So what I'm going to be doing here is I'm going to be solving every single gate theory exam question. And if we go through all of them all the way until the very, very end, there are quite a few exam questions, 247 exam questions. So without further ado, let's actually get started. So what I'll try to do is I will try to not go too in depth into them and leave those to the exam questions videos where I go into in depth into the particular question in mind. But here I'm just going to give a brief overview of the solution. Okay, let's just make sure everything's set up. So this first one is, if L is a regular language over AB, which of the following is not regular? We actually solved this before in a previous video, and it turns out it's B. And the reason it is B, you can do by process of elimination, because regular languages are closed under reversal and concatenation. So D is regular, L is regular, L reverse is regular, their concatenation's regular. Prefix is regular because what you can, and suffix is regular for the reason that if you take a DFA or whatever for L, what you can do is you can have an epsilon transition from some state from before to the exact same state in the second one on epsilon, which allows you, for example, for suffix, what it allows you to do is to instantaneously jump into the second machine so that you can read the Y part instead of the X part. So that's essentially the idea. And B is not regular because it's essentially palindromes, and you can show it's not regular if L is sigma star, for example. Then palindromes over this is not regular, and the reason is that you can pick the string S to be, so it would be A to the P, B to the P, B to the P, A to the P. You can only pump in the first P characters here, so that would cause the string to not be this to be a palindrome anymore, because either fewer or more A's will cause the number of A's at the end to not match. So B is the correct answer here. Okay, and another thing I should say is that I have not seen any of these questions before, other than the ones that I've done before. So most of these I have not seen, so I'm going to be doing this completely blind. So let's see. So we have a regular language here, with strings of the form a to the multiple of 3 plus 2, or b's being a multiple of 12 plus 10. Which of the following can be can be a pumping length, the constant guaranteed by the pumping lemma for L? Well, I don't think it can be 3, because you need to have at least 12. So then for that reason, I don't think it's any of these 3. So I think it's this one. Because in order for this one to get the ones that are a multiple of 12 plus 10, you need to have at least 12 states to start with. So D is the answer for that one. Okay. Consider the following sets. Set of all recursively enumerable languages over 0, 1. All valid C programs, all languages over the alphabet, 0, 1, all non-regular languages. Which ones are uncountable? So we can actually do this directly, I think. So valid C programs, that is at most the number of all possible programs, which is corresponding to all binary strings, which is a countable set. So S2 is not going to work. S1, recursively enumerable, that corresponds to Turing machines, so in which are countable. So S1's not included. And we can actually see that each of the answers has two of them, so it has to be S3 and S4, I'm pretty sure. Yeah. And we can actually see that because all languages are uncountable. There are uncountably many languages in total. And non-regular ones, well, if you exclude DFAs, which is a countable set, from an uncountable set, you'll be left with an uncountable set. So B is the right one there. Which of the following is not context-free? We did this one before. So it is B in this case, from what I remember, because A is all palindromes, and you can make a palindrome with a context-free grammar like this. This one is going to be S goes to ASB, or ASBBB, or AS with 5 B's, or empty, because the I here involves. Actually, no, it's not quite that easy, but I claim it's context free because you can have a variable that does the n part, another variable that does the 3n, and another variable that does the 5n. In this one, you can modify this grammar, and instead of going to empty here, you go to another variable that makes the a to the n, b to the n part. So you can recursively go down into the a to the n, b to the n part. Whereas this one you can't, because the a to the n and the b to the n parts are far apart from each other. So, and you can actually prove that that one's not context-free. I think we did a video on that before. So consider the language. This one, which is any, so it's basically A star, union, A to the n, B to the n. L, so which of these statements is true? So L is deterministic context-free. So is it deterministic context-free? Yes, because, so I would say 1 is true because the DPDA for it would read the A's, push them onto the stack, and if it happened to read a B afterward, then it would proceed to a part where it pops up all the B's and tries to match them up. L is context-free but not deterministic context-free. No, because we know it's deterministic context-free. L is not LLK, so essentially what that means is, like, can we actually look forward K characters? And it's not, because we can have the N grow as large as we want. So this one is also true, so it's 1 and 3. I think we did this one too. If the union of two languages is regular, then both must be regular. No, because we can have L not regular, and L bar is also not regular by closure and complement. And we know that L union, its complement, is sigma star, which is regular. So that one is not true. Class of regular languages is closed under infinite union. That one's also no, so neither is the answer for that one. Which of the following regular expressions represents the set of all binary strings with an odd number of ones? So let's see. With an odd number of ones. Well, this one won't work. So this one won't work because you can never have two ones next to each other in this one. Let's look at the last one. Same idea. That one can't have two ones next to each other. Same thing with this one. You can't have two ones next to each other. So B is the answer then for that one. And the reason for that is that the 0 union 1 star here can take care of additional ones if needed. Is that right? Yeah, because of this. So this star right here is the key, because it allows you, because we can guarantee that that the number of ones produced in here is even because of these two ones in here. So that this one extra will give us allow us to get an odd number. Okay, so that B is the answer for that one. We did this one too. We did a lot of the early ones, the 2020 ones, it looks like. So which of these are undecidable? So this one is ETM, so that one's undecidable. This one is not undecidable because it reaches state Q in exactly 100 steps. So what you can do is just simulate it for that long. So that one is decidable. L of M is not recursive. So that means that it's not. Yeah, so that one's undecidable too because there are some languages that are recursive, some languages that are not. And the fourth one you can get via Rice's theorem, so it's D here. Okay, the number. So all the strings in A, B star such that the number of A's and X is divisible by 2, but not divisible by 3. Okay, so this one was just a fill in the blank, I guess. And the reason for it is, if it's divisible by 2, and it's not divisible by 3, well, that means that it's divisible by 2 for 8, 10, 14, 16, etc. Well, the number of A's is this many. So that means, because we would need to be able to figure out that we have hit 6 characters, 6 A's in order for this to determine that we hit the not divisible by condition. So you do need at least 6, and you can accomplish it with 6 by just determining the number of A's modulo 6. Consider the following languages. Which of the following is true? So we have WXYX, where WXY are non-empty strings, and XY, where they're not equal. Which of the following is true? So L1 is context-free. Yes, I think so. Context-free, but not regular. Actually, I'm not sure about that. L2 is context-free. So this one I'm not sure, maybe. Neither is context-free. No, because this one is context-free, so this one is context-free. And it's not regular because X is not equal to Y here. And you can show that with the pumping lemma, so not regular. So A could be true, B is not true, C could be true, maybe. D is not true. So then let's figure out A here. Let's see. Well, we can actually have the W and the Y part be anything, and the X string be like one character. So I claim that this one's regular too, because you can, by having W and Y be as long as we want, then the X part can just be one character, and in fact we can be left with, I think, a finite number of strings that we don't get out of it. Yeah. And then if you take sigma star minus a finite set, you would always get a regular language out of it. Cool. So I would say that it is regular, so that means that this one is not, so it's C in that case. Okay. Let n be an NFA with n states. Let k be the number of states in a minimal DFA, which is equivalent to n. Which of the following is necessarily true? Well, it can't be more than 2 to the n by the product construction. So D is the answer to that one. But it can be certainly less than 2 to the n. Set of all recursively enumerable languages, so think recognizable languages. It's not closed into complement. It is closed into intersection. Is a subset of all recursive? No, it's a superset of them, so that's not that. It's not an uncountable set because, as we said earlier, they correspond to Turing machines, and those form a countable set. So B is the answer there. This is the one that we actually just did in office hours earlier today, believe it or not. So this is actually a very interesting question, which is we're going to define L to the I as being, it's kind of like the star operator, where L to the 0 is the empty string, and L to the I is basically, L to the I just means I concatenations of L with itself. And the order of a language is the minimum K, such that if you concatenate L again, you're not going to get anything different. Consider the language accepted by the following automaton, which is this one, and what's the order of it? Well, what we can see here is the language of this machine right here is the empty string, and then because of that state, and then from there on, we can get all odd length strings. So we can get the string of length 1, 3, 5, etc. And then if we concatenate L with itself, well, we must be able to get the empty string out of it. And we must be able to get the string, so we must be able to get all of these strings, because we can just concatenate empty string onto all of these other ones. So I can get the string of length 1, but with this string of length 1, I can concatenate it with any of the other ones to get every even length out of it. So I can get the string of length 2, 3 comes from 3 and the empty string, 4 comes from using the 3 and the 1, and in fact we can get every string length. So this is actually equal to sigma star. So then if we apply the concatenation onto sigma star, you can actually show that we still get sigma star out of it. So the order is actually 2, because LL is different than the original one. But if we apply, so this one is equal to L squared, it's the same thing. And then this one is equal to L cubed, but we can see that L squared is sigma star, L3 is sigma star, so the order must be 2. Okay, oh, this one looks kind of complicated. So let's see. Which of the following languages are context-free? Well, I think I can see that 3 is not, because M equal N equal P, that's not gonna fly, because you can't have 3 counts in a row that are the same. What about for 4? Let's see. Well, 2 is, because you can have one variable make the first 2, and another variable make the second 2. One is because, yeah, because what you can do is, so I'm going to leave a few details out, but what you can do is push on A's, or at least keep the absolute value of the difference between M plus P, which is the number of A's and C's that you see, and the difference between that and the number of B's and D's that you see, which is N plus Q. And then you accept if that difference is exactly 0, and you can keep track of the difference in the stack. So what you can do is, if you see like another C, you push onto the stack, and then once you see a D, you pop off the stack. So you keep a track of the difference. So this is actually a good example of where you can apply deductive reasoning here, although I don't recommend it, because every answer has 2 of these, and we determine that 2 of them are context-free, so it must be 1 and 2. Okay. L-G denotes the language generated by a grammar G. Oh, we know that. which of the so it's looking at a bunch of languages or problems and figuring out whether they're decidable. The third one I can immediately see is undecidable. Maybe I should denote it by undecidable, because that's EQ-CFG, which is undecidable. 2 is undecidable by Rice's theorem. For an unrestricted grammar G, 4 is undecidable, because if you have the NFA have sigma star, that's asking if the PDA's language is sigma star, but that's undecidable because of essentially the same reasoning as EQ. So let's see. Oh no, I didn't see this. I didn't see this. I didn't see deterministic. Okay, that makes a total difference. Yes, that is decidable. That's an interesting problem. That is decidable because L of n is equal to L of p if and only if L of n intersection p's complement union L of n complement intersection L of p is the empty set. And what you can do is, so this is deterministic context-free. This one's also deterministic context-free because the intersection of a DCFL and regular language is deterministic context-free. The union might not be a deterministic context-free language, but the union is always a context-free language because CFLs are closed under union. And we could check whether grammar, for example, has empty language or not. So that one is decidable. Nice. And okay, yeah. So 1 is equivalent to a Turing machine, and that's asking whether a string is in the language of that grammar. So it's undecidable too. So 1, 2, and 3 are undecidable. Okay. So we got a grammar here, and we want to, which of the following represents the language generated by the above grammar? That contest-free grammar. So let's see. So T makes, so the language of T is, well, let's see. It's b to the n where n is at least 1. So the language of S is A, B, C, b to the n where n is at least 1. So that corresponds to the second rule. The first one is A, B, S, C, b to the n. So effectively, what we're doing here is we're having something like A, B to the n kinda C B to the something else, and then C B to the something else. Yeah, so it is this one, because we can repeat this as many times as we want. And they're all at least 1, so it's B in this case. Consider the language with a regular expression. Smallest number of states for a DFA, accepting it as something. So what is it? So it's, can we, let's see if we can actually do this in general. Let's actually try to make a NFA for it and see what happens. So yeah, so let's see. So this is what an NFA for it would look like. Well, if we did, so that's Q0, Q1, Q2. So if we did the power set construction, let's see what would happen. So if we have A, oh no, that's not a final state. Yeah, that's not a final state. So then B would give us Q0, Q1. A would give us Q0, Q2. Where would B give us? B would give us Q0, Q1, Q2. Q0, Q2 would give us, would go back on A like that, I think. And go back to here on B. Q0, 1, and 2 would do the same thing that Q0, okay, yeah. Would do the same thing that Q0, Q1 did. So that would, so the states, final states are the ones that include 2 in them. Are there any, yeah, so we can accomplish it with 4 states, I think. Yeah. Good. Because the smallest answer is 4, and we got it with 4 states, so that's good. We got a grammar here, and which strings are not generated by this. So this one can we get 3 A's? Let's see. Yeah, we can get 3 A's because we can apply this rule as many times as we want and have S go to empty, so that one can go. This one can, which means this one can't, so this is the answer. But why is it the answer? It's the answer because there are more B's in this string than A's. And every rule has either the same number of A's and B's or more A's. So this string cannot possibly be made. Consider the CFGs over the alphabet. S and T are non-terminals. What is the language that is the intersection? So for G1, so the language of G1 is A to the N, C to the M, B to the N, I think, where N and M are at least 0. Yeah. L of G2 would be B to the N, C to the M, A to the N, where N is and M at least 0. So the only strings that would be in there, oh yeah. So the only ones that would be in there are where N is equal to 0. But M, the number of C's, can go as big as you want. So it's B, because it's equal to C star in that case. Okay, let's just make sure that everything is live. Okay. Looks like we're good. Maybe I need to change the name. Let's see. I'm changing the name of the live stream. Okay. So consider the following languages. Which of the following are context-free? So we got... Oh, okay, so this is a classic problem. So if we have the same number of A's and B's and the same number of B's and C's, then that would imply the same number of A's and B's and C's, which is not context-free. So 2 is not context-free for sure. 1 is context-free because you can make a grammar for each one of these. And the reason is that you can have a variable that makes the A to the N, B to the N part, and another variable that just spits off C's at the end, and another grammar that does almost the exact same thing, and then just union the two. So 1 is context-free, so it's A in this case. Let's just check. Yep, good. Let A and B be finite alphabets, and let pounds. Leo, do you need to get out? You need to get out? You need to get out? They just don't need to get out. Okay, so let pound sign be a symbol outside both A and B. Okay, let F be a total function from A star to B star. So total function just means that every string in A star, F of that string is defined in B star. We say F is computable if there's a Turing machine which, given input X, halts with F of X. Let else of F denote the language X pound sign F of X. Which of the following is true? So let's see. So let's see. So if F is computable, then it's decidable. And if L of F is decidable, yes. So it is A. I can immediately see that it's A. Why? Because if F is computable, then I can compute F of X. If I'm given X, I can compute F of X. So that means that why is L of F recursive if F is computable? Then what I can do is I can take the function, apply the input to it, and then just write it out onto the tape. Well, consider the other scenario. If L of F is recursive, so we can decide whether X pound sign some string is in there, then how can we actually compute Yeah. So what can we do? Well, if L of F is recursive, that means that we can decide in a finite amount of time whether some string that is in this set L of F. Then how can we compute F when we're given just input X and nothing else? What we can do is just iterate through all the possible strings, and that could be the candidate string right here. And then just repeatedly ask, is this the output F of X? Is this the output F of X? And just keep trying. Because F is total, that means that X has a defined string somewhere. So that means we can just keep trying strings over and over and over, keep getting bigger and bigger strings. At some point, because F is a total function, we will hit it eventually. Well, that's a pretty cool problem. So it is A here. So the key thing to notice here is that it is a total function, and so one direction is easy. If F is computable, then we can just figure out what F of X is, just compute it, and then write it out on the tape. And the other direction is a little more complicated, but you gotta use the fact that it's a total function. Let L1, L2 be any two context-free languages, R be any regular language. L1 union 2 is context-free, yep. L1 bar is context-free, not necessarily. L1 minus R is context-free, yep, because L1 minus R is equivalent to saying L1 intersection R complement. R complement is regular, and the context-free language intersection a regular language is context-free. And 4 is not context-free because CFLs are not closed under complement. So it is 1 and 3. God, only on question 23. Identify the language generated by the following grammar. S is start. So X is just any number of A's, at least one. So, and then Y is... Okay, so it must be one of these two, because we can't have the number of A's be the same as the number of B's, because The X part must make at least one A. And we could have 0 B's. So it's, I think it's C. If I'm, let's see, let's just make sure. Yep, it is C. Good. Minimum possible number of states that accepts this regular language. So let's just do it the old-fashioned way, make a NFA out of it. Oh, no, that's not right. So the length of the first part is 2, and the length of the second part is at least 3. So that means that the number of states is at least 6 for this to even work. Okay. Okay, let's think about this. Okay, yeah, because it's a DFA. Okay, so I see what to do. So what we can do is, I don't care what the string actually is for W1, but once I get to here, if I have a B at that point, because of this A right here, I need to go to a state where I never accept anything. And then here I must read an A. Then I must do any A and B's here. And then here it goes to a final state. So that's 8 states. So, and that's the smallest possible answer, so it's 8. And you can actually see that it's the smallest possible, because if any transition goes back, then we would accept more strings than we are allowed to. Let delta denote the transition function, delta hat be the extended one of the epsilon NFA, given by this. Then extended transition function of ABA is what? So what's the transition function from Q2 on, let's just go one character at a time. Well, Q2 on A, oh, that goes nowhere. Is it really nowhere? Q2. Is it really Q2? Q2 on. Yeah, I must. Oh, okay. Because of the epsilon transition here. Okay. So, okay, it goes to Q0. So the epsilon closure of Q2 is the set Q0, and it doesn't go anywhere else on epsilon, so it just has Q0, Q2. So because Q2 goes nowhere on A and B, so what we need to do is calculate delta of Q0A, which is Q1, and we gotta include Q2 and Q0 into the epsilon closure. Yeah, so then delta of Q0, maybe I'll write them together. So Q0, Q1, Q2 on B, so these are including the epsilon closure. So Q2 goes nowhere on it, which is fine. Q0 on B goes to Q0. Q1 on B goes to Q3. And that's all we can do. Q0 includes the epsilon closure to Q2. Yeah, Q2, Q3. So delta of Q0, Q2, Q3 on input A. Well, Q2 does nothing, Q3 does nothing because there's nothing here for A. Q0 on A goes to Q1, but that will include Q0 and Q2. So I'm going to go with C on that one. Yes, good. Consider the following languages. Let's see how many viewers we have. So for those of you who are watching, we are solving every single gate theory exam problem all in one set without stopping. And we're only on question 26. Okay. L1 is context-free but not regular. No, because this language is not even context-free. L2 is not context-free. That is not true because it is context-free. L3 is not context-free but recursive. Yes. L4 is deterministic context-free. Yes. So I would go with 3 and 4 here. So I would say D. Which of the following are undecidable? Given a regular expression, that's not undecidable, that is decidable. Is the grammar's language empty? No, that is decidable. Given a CFG, is it equal to sigma star? That is undecidable. Given a Turing machine, is it in there? Yep. So it's 3 and 4 again. So I think this one's also D. Good. 28. Which of the following languages is generated by this grammar? Well, it generates everything, it looks like. So it's not A, not B. Yeah, so it must be D, I think. Yeah, it must be D. I don't know why that question seemed harder to me, I guess. Which of the following are undecidable? Given NFAs N1 and N2, is the intersection empty? No, that is decidable because the closure in the intersection helps you there. Given a CFG, does X belong to the language of the grammar? That is decidable, so it's not undecidable. Given two grammars, are they equal? Yes, that's undecidable. Given a Turing machine, is it equal to empty? Yes, that's undecidable. So I would say that this is 3 and 4 also. They switched it up on me, so it's going to be C this time. Which of the following regular expressions gets the language? Set of all binary strings having 2 consecutive zeros and 2 consecutive ones. Oh boy. Okay, so let's actually figure this out. Well, this one does not work because the consecutive zeros and ones don't have to be next to each other. B I'll come back to. That looks a little complicated. C does not work because this plus in the middle gets you. Because it can't be like it's one or the other one. It must be both. D doesn't work because it doesn't have to start with 0, 0, and end with 1, 1, or the other way around. So why does the other one work? Okay, yeah, it works because B solves the problems that this last two didn't, that the last two had, because it can be anything before and after, and what could happen is the 0, 0 is in one place, and then later was 1, 1 appears, or the other way around. So B is the right answer here. Okay, got CFGs here. Which of the following pairs of languages is generated by G1 and G2? So G1 gets is A to the N, B to the M, I think, where N and let's see. N is at least 0, B is at least, it's going to be a long night. N is at least 0, M is at least 1. G2. So the first one is not right. Yeah, the first one's not right. Second one's not right because the wrong condition for the number of A's here. So it actually must be D. Because we don't even need to look at the second one. Based on the condition, D has to be the only possible answer, because both of the two conditions have to be satisfied. Okay, we got a PDA here. I'm not sure of this notation. Z is the initial stack symbol. Okay, I'm not sure what that means. I'm guessing that's what it starts off with. Let L denote the language accepted by the PDA. So I'm guessing what this notation means is it reads an A, pops an X, and pushes on two X's at the same right then. Let's see. I'm not sure what any finite automata means. I think that just means DFA or something. Oh, okay. This was actually the machine that we saw earlier. Or at least the language was. Because here we can just yeah. So what we can do is we can just repeatedly apply this second transition here, and which just makes the stack grow bigger, and we don't really care. So this gets us A to the n. Union, well here, this pops off x's for every b that it sees, and we can only go to this final state if we if we matched up the a's and b's, which is this. And it's deterministic context free because all of the transitions are incompatible with each other, because these two transitions can't be done at the same time as this one because this reads a B and these read A's. These two can't be done at the same time because different pops, and these two can't be done at the same time because different pops. So it's deterministic context free. So would C work? Why wouldn't it work? No, because we saw that it must halt. So C is not true. Not accepted by any deterministic PDA. This is a deterministic PDA. And this one's not true because the language is wrong. Okay, let X be a recursive language, so recognizable. Y be, decidable. Y be recursively enumerable but not recursive. W, Z be two languages such that Y, okay, Jesus. So Y bar reduces to W, and Z reduces to X bar. Standard meaning one reduction. Which of the following is true? So X bar must be recursive because of closure under a complement. Y can be anything. So I don't think that implies anything about W. Well, Z is recursive because we can apply the reduction, solve the problem over here, and then solve the one for Z. So, so D is not true. What about W? So Y bar must be not recursively enumerable. Yeah, because of closure under complement. Y bar reduces to W. Oh, yeah. W can't be recursively enumerable. Yeah, cannot be recursively enumerable. Why? Because if it were, then that would imply Y prime is recursively enumerable. Because what we can do is just apply the reduction, solve the problem over here, and it would give you the same answer. So A can't be true. Yeah, B can't be true because that would imply Y is recursive, so C is true. Cool. Number of states in the minimum size DFA for this language would be... oh, so this is all non-empty strings. So I think you can get away with 2 states. Yeah, because what you can do is this. So it's 2. So this one, yeah, so this one is Is L1 regular? No, because that's A to the n, B to the n. L2 is regular because that's just A, B, whole thing starred, and that's a regular expression. So P is false and Q is true. So that would be C in this case. Consider the following types of languages. L is 1's regular, 2 is context-free, 3 is recursive, 4 is recursively enumerable. So 3 is true because L1 star is regular. L1 union, we don't know necessarily that's true, so it's false. L2 union L3 is recursive, so that's true. L3 union L4 is recursively enumerable. So 1, 2, and 3 I'm going to put into here. Yep, good. If all the states in the NFA are accepting, then the language of the NFA is sigma star. Nope, that's not true. There exists a regular language system for all languages A, B. Okay, we did this one. If A is the empty set, then A intersection B for any language B is the empty set, which is regular. So 2 is true, so only 2 is true. So that would be that one. So which ones are context-free? L2 is not context-free. Yeah, L1 is context-free because if you think about it, we can break up the string like this, where what we can do is push on the A's, push on the B's, and then pop off the C's later, and then try to accept if the counts are the same. So L1 is context-free, L2 is not. So B is the answer there. Okay. We did this one. Actually, this was the first one I did. Which of the following is true? Which ones are recursive, which ones are not? So L3 is not recursive. And the key to... So this was actually a hard question. So the first two are recursive. Why? Because if it takes at least 2016 steps on some input, then all we need to really do is to test all strings up to length 2016. So L1 and L2 are both recursive here. Purely because on some input, we can just test all the strings up to length 2016, and if any one of them takes at least 2016 steps, then we're good. The reason we can limit to 2016 is if the input length was longer, because the Turing machine starts at the left-hand end, it has to go right. It has to progressively move right through the string. And it can't hit the 2017th character. Well, I guess the 2018th character, but you know what I mean. It can't get to the 2018th character and beyond. So we can limit the size of the inputs that we consider. And L2 is the same logic, except now if any one of the inputs doesn't take that long, then we reject. Then otherwise we accept. So the first two are recursive, and the third one isn't. Student wrote 2 context-free grammars. Okay, this is weird. The dimension of an array, blah, 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 blah. Which of the grammars correctly generates the declaration mentioned above? D is the start variable, it looks like. Let's see. So G1 works because int A bracket, then go down to the E part, which can go into num and then close it off, or restart it again. So G1 works. Does G2 work? Yeah, because it's going to be generating the square bracket nums from the right side instead of from the left side. So G2 also works, so A is the right answer there. For any two languages such that L1 is context-free and L2 is recognizable but not decidable, so not recursive, L1, complement of L1 is recursive, that's true. L2 is not, so that one's not true. Um, L1 bar is context-free, nope, not necessarily. L1 bar union L2 is recursively enumerable. Yep, so it's 1 and 4 here. Given the DFAs right here, what is the minimum number of states accepting the language intersection? Oh, so this is actually an interesting question because let's look at this. So how do you get to the final states here? Well, in this one, you have to end with an A in order to get there. In order to get to B, this one, you have to end with a B. We notice this, that all transitions that end in A go to this state, and all transitions that end with B go to this state. Well, there's no string that ends with an A and the B at the same time. So, therefore, the intersection of the two is the empty set, and we can accomplish that with one state. So that gives us one state. Given a non-deterministic PDA, where Q is a set of states, we have a state transition here. Which of the following sequences must follow the string so that the overall... Which of the following sequences must follow the string 101100 such that the overall string is accepted by the automaton? I'm not sure what must follow the string means. Does it do the same states? So let's see, where does it go? Must follow the string. So let's see. We see a 1 at the beginning, so we must push on a 1 onto the stack. So we have Z and then 1. So that means that these two... Well, no, not necessarily. That's not necessarily true. Oh boy. Let's see. Oh, I think this is figuring out whether we have the same number of zeros and ones. Oh, no. That's not right. It's doing palindromes. Yeah, it's doing palindromes. And because of these two transitions at the end. Okay. Well, this one is not a palindrome, so any one of these strings that's a palindrome won't work, so C won't work. 1, 0, 0. Oh, no, it's not exactly palindromes. Never mind. Because of the 0 and the 1 here. Zero. This one's... I've never seen this one before. Well, if we think about it, we must get either 0, 0, W reversed, or W1, W reversed, or WW reversed. Um, and this string doesn't follow either one of those because it must be this one, and it's not. It's not a palindrome. So yeah, so this one won't work because it fits into this convention. Um, but the last one does. Why would that work? Oh, it's not the reverse. Oh, okay. Yeah, because of the 0 1s here. I thought that was reverse. So it's substituting. So it must be something like this. So where x is the w reverse, but switch 0 and 1 here. Yeah. So this one won't work. The last one might work because you're just switching the 0 and the 1 on both sides. B might work for the same reason. And A might also work. Let's see. Which of the following sequences must follow this string? So the overall string is accepted. I think all of them can. Well, the first, second, and the fourth one can, for sure. Um, yeah, I'm not sure. I'm gonna skip that one. Let me know in the comments for those of you who are watching, um, what you think the answer is. Um, okay. Consider two decision problems such that Q1 reduces in polynomial time to 3 set, and 3 set reduces polynomial time to Q2. Q1 is in NP, yep. So and Q2 is NP hard, that is definitely true. Q1 is an NP. Wait, those two are the same answer. Um, yeah, but yes, because if it reduces the 3 set, it must be an NP. Okay, I'm not sure what that's supposed to mean, but I think A is the answer there. I'm not sure what these three are supposed to do. Complement of every decidable language is decidable. Which of these is true? So 1 is true. There exists some language in NP which is not Turing decidable. Note that's not true because we can simulate all of them in a finite amount of time. If L is an NP, it is decidable. Yep, so it's 1 and 3. So it's D. Okay. Which of these are regular? 2 is not regular. I can see that immediately. L3 is regular because there's no dependence. Um, um, Okay, yeah. So the key here is that X can be anything. So what you can do is you can have W be a single character and X can be anything. So this is just asking if the string starts and ends with the same character, which is regular. So 1 is also regular too, so it's 1 and 3. Cool. Minimum number of states in the DFA to recognize this. So this must be... It ends with 1, 0, so that means that we can do it with 3 states because we can do something like this. So 1, 0, and then if this sees a 0, it'll have to start again. If it sees a 1, it can go back here and try again. If we see a 1, we stay here, and if we see a 0, we stay here. Yeah. Consider the alphabet. So we have a regular grammar here, which, oh Jesus, I feel bad for you guys who have to deal with this type of thing. The strings in X0, so it must start with a 1. Okay, that doesn't help us. Well, at least it doesn't go back to X0, which is nice. Let me write this out. So S0 goes to 1, S1, S1 goes to 0, S1, or 1, S2, S2 goes to... This helps me look at it in a different way. We can't end with a 0. That doesn't help. How can we get this? I mean, we can convert it to a NFA and then convert that to a regex, but that's not the point. And that actually wouldn't help very much. So we can actually think of this as S0 goes to 1, S1, that doesn't change, 0, S1, or 1, 0, S1, or 1. It's just sidestepping S2 altogether. So does that help? Ah, yeah, it does. C is the answer, because this is 0 with 1, 0. Ah, that's nice. I guess that's the trick. To actually see that we can actually remove S2 entirely just by moving the rules up. Okay, cool. Let L be the language of a regular expression. What's the minimum number of states in DFA that recognizes the complement of this? Oh, Jesus. So, let's see. Let's actually, well, we can just, we can convert, oh yeah, okay, let's just make a DFA for this. So let's just make any old DFA for this. So if it ends, so if it has a 0 or 1 here, then we can, if it has a 1 here, we can stay. If we have a 1, we go back. If we have a 0, then we can stay, I think. And then if we have a 0, we must go here. And then we can complement to get the right DFA for the complement, so we can get 5 there, because this thing has 5 states. Okay, L1 poly reducible to L2, L3 reducible poly time to L2, which is reduced to L4. So if L4 is in P, L2 is in P, that's true. Yeah, that's true. If L1 or L3 is in P, then L2 is in P. No, not necessarily. L1's in P if and only if L3 is in P. We don't know anything about their relationship. If L4 is in P, then either L3 or L1's in P. That is true because it's propagating back either this route or this other route. So it's 1, 4. Which of these two is context-free? Let's just make sure that this is still going. Yep. Okay. Which of these three is context-free? M is equal to 2n plus 1. So L3 is. L2, no, because of reasoning that we did earlier. And L1 is because we can have a variable that makes the outer two pieces and then recursively goes down into the inner two. Because the counts don't have anything to do with each other. But the second one, the counts, can be far apart from each other. So the answer there would be L1 and L3. Which of the following is true? That one, language is regular? Nope. Language is prime is regular? Nope. Language has 3k plus 1 b's for some k. So that just means then odd number of 3's plus 1. Yeah, so that's regular. And the fourth one is not regular. And that's easy to show. So C is true. Which is C. What's the set of reachable states for the input string 0011? So 0 takes us to Q0. So with another 0, we go to Q0. 1 takes us to Q0, Q1. Another 1 takes us to Q0, Q1, Q2. So I think it's A in this case. Yes. L1 and so is A and it's in B's. So 1 is true. So this is just testing about whether you know concatenation. So both are regular, so the concatenation's regular. They're not. It's not this because the string that you pick out of here and the string you pick out of here can be totally different lengths. So it's only 1 in this case. Only 1's true. Mapping reducible. Okay. So let's see. If A maps, then B is recursive, then A is recursive. So it kind of gets you with mapping reducible. If B is recursive, then A is recursive. Yeah, I think that's true. Yeah, I would say that one's true. Because you can just do the reduction and then B, and then solve it with any solver for B. If A is undecidable, then B is undecidable. Yeah. Oh, no, which one's false? Oh, okay. So it's not this one, not this one, because B is essentially the same, the contrapositive of A in some sense. If B is recursively enumerable, then A is recursively enumerable. So that's true. So the answer, that's not the answer. So it must be D. If B is not recursive, yeah, okay. So this is, if this was A and this was B, then it would be true, but it's not. Okay. So let's see. Let M be encoding of a Turing. Let me actually turn off notifications just to be sure. Let M be the encoding of a Turing machine. L what do we know about L? Then it's undecidable via Rice's theorem, and it is recursively enumerable because we can just, in parallel, simulate all strings of length 14. So B is the answer. W has at least as many occurrences of this and that. Okay, so this one's actually quite complicated. So this one you can actually show is not regular via the pumping lemma by picking the string that looks like this, and then always pumping down. So that one's not regular. So what about A? I mean, in a paper that I did a few years ago, we determined what the condition was, but I'm sure, well, it wasn't done when this test was made, so I can't assume that you guys know that. All right. As many as 110s as 011s. Well, it's deterministic context-free for sure, but that doesn't tell us whether it's regular or not. Well, let's see. Let's see if we can try to make a DFA out of this. Well, if it starts with 1, 1, oh, that we should accept always at that point. Okay, because the 110 would always be may or may not be satisfied. We don't really care. But the 011 would never be satisfied necessarily. Yeah. And for these states right here, they should also be accept states because here the empty string satisfies this, the string of length 1 satisfies this, and so on. Yeah, that's good. What if it starts with a 0? Same story. What if it starts with 1, 0? Okay, yeah, so that would have to go here. So I'm collecting all the states where the last character is a 0 right here. And then if we read a 1, 1, that should go to a non-final state. And then if we read 1s, we should stay there, and then back on 0 to restart the search again. And same story here. Yeah, that works. Yeah, because that's just determining when we've actually seen a 011 and not a 110. Yeah, so if I make it here and take the 0 back, then that means I've seen a 110 that just matched the 011 that I saw taking there. So that means that we have the counts matched up again. So that means that L1 is regular. Oh, that's nice. So L1's regular and L2 isn't. Cool. Shortest string not in the language of the regular expression is what? So let's see. Maybe we can try generating strings. I can get the empty string out. I can get A. I can get B because all the stars over on this side. Can I get AB? Can I get AA? Yes, I can. Can I get AB? Yes, I can. Can I get... Oh, I can get BA, that certainly. Can Can I get B, B? Yep, because of the star there. So it can't be all uniform characters, whatever the shortest string is. Can I get... So let's try AAB. Can I get that? Yeah. Can I get ABA? Yeah, I can get that. I don't think I can get BAB. Can I get BAB? Well, if the first B is generated by this, then I need to get AB, which I can't. If this was, yeah, I can't get BAB. So 3 is the minimum length. Cool. Let sigma be the power set of sigma star. Sigma star is always countable. So this is not the answer. This is not the answer. 2 to a countable set will an infinite countable set, because it's non-empty, will be an uncountable. So C is the answer there. Which of the following is undecidable? Checking if the CFG is ambiguous. That's true. Okay. 2 CNF sat. I don't think we can actually solve this here, because it is solvable in polynomial time, so that one's true. Solvable in constant time, no, so that's not true, and that's a complicated reason why that's true. NP hard but not NP complete, that's not true, because it is an NP. It might be NP complete, but we don't know the answer. So P is not equal to NP. So I would say that the true answer could be either one of these, but B is definitely true. So A could be true, it's just we don't know the answer. Yeah. Consider the following languages. Which of these are deterministic context-free? L1 is. This one is. And L3 isn't, I think. Yeah, L3 isn't. Because we can't non-deterministically guess the middle. So only L1 and L2 are. So suppose you want to move from 0 to 100 on the number line. Each step you move right by a unit distance, or you take a shortcut. The shortcut is specified by 2 integers. You are at position I, you go to position J. TK is the smallest number of steps needed to go from K to 10, 100. There's at most one shortcut involving any number, and in particular from 9, there's a shortcut to 15. Let Y(Z) be such that, what the frick? Be such that T of 9 is equal, what is T? Smallest number of steps to get from 9 to 100, okay. Then the product, what in the world? Okay. So T of Y is the min number of steps to get from Y to 100, and T of Z is the same thing from Z to 100. Let's see. Okay, so we can always move right by one element. So let's see. So Y is 10, or could be 15, and Z is the other one, which is 15. So Y and, okay, so it is 150. Okay, that's a really in-depth problem for something that's kind of easy. Okay. For every non-deterministic machine, there's an equivalent deterministic one. Which of these is false? So it's not that one. Um, recognizable, so 2 is false. 3 is true, so it's not the answer. 4 is true, so it's not the answer. So it's only 2 in this case. And the reason for that is that if for all the other operators, we can just simulate in parallel. The problem of determining whether there exists a cycle is in P, so that's true. Which of these is true? Okay. Determining whether it exists a cycle is in NP. Yep, that's true. For problems NP complete, there exists a non-deterministic polynomial time algorithm to solve it. Yep, so that's true. So all 3 are true. So we have a DFA right here. Complement of L, which is false, so that's not true. I mean, it is true, but it's not the answer. The language of A is whatever. Maybe that's true. Or false. For the language, A is the minimum DFA. Yeah, that's pretty easy to see, so that's not the answer. A accepts all the strings of length at least 2. So that's definitely not true because of this loop right here. So 4 is possibly the answer. What about 2? Okay. Okay, so this part is saying the 2 possible paths you can take to this state, and then 0 plus 1 star will give you the rest. Okay, yeah, so this one is true, so it's not the answer. Wait. Can we make a smaller DFA? Let's see. Oh yeah, okay. I was thinking way too hard. Yeah. So yeah. So you can take one or more transitions here. So in fact, we can minimize this. That was my mistake. So that should be true also, because we can make a NFA that I mean a DFA that looks like this. So it is 3 and 4. God, I'm only on 67. Which of these is undecidable? Not that one. Yes. Yes. No. So 2 and 3 is undecidable. Okay. So this one is A star. So it should be the empty set. Oh, no, not the empty set, because it doesn't get the empty string. But it gets every non-empty string. Okay, so it should be B here. Which of the following are decidable? Does a given program ever produce an output? No, that's not decidable. No. Yes, that's true. Recursive is also recursive. Yep. So 3 and 4. Which are the following strings? Oh, Jesus. A, B, A. So 1 is... That 2 is... A, B. I don't think 3 is. Okay, let's try 4. Let's just be sure. B, A, B, A. Yep, so 4. So we can say 1, 2, 4. Good. So there's a set of strings. push missing arcs. Partially completed. Every string has at most 2 zeros. Let's see. The missing arcs in the DFA are what? Maybe zoom out a little bit. 0, 0. Well, 0, 0 is clearly missing stuff. It's just to what, though? Okay, so it's just recording what the last two states are. I mean, the last two characters are. Okay, so if it sees a 0 from 0, 0, then that means it's seen 3 zeros in a row, which means we should not accept, which means we should go to Q. So these two are not the answers. The 0, 0 stays the same between the two. What about 0, 1? So 0, 1 on 1, we should go to 1, 1. So in fact, this is not the answer, that's the answer. So it's just recording what the last two characters are. Okay. Let P be a regular language and Q be a context-free language, such that Q is a subset of P. Which of the following is always regular? Sigma star minus P, so that's always regular. Let's just be sure of that. Yep. We can't involve Q in any way. Different expressive power? Nope. Yes. The F should be a D here, I think. Nope. Nope. So it's B. Because closure and complement for one and not the other. A to the NK. What is the minimum number of states? Oh, okay. So this is just, yeah, it's just n plus 1. Yeah, because we can just make a, yeah, so we would need a cycle of length n, then plus 1 state. Yeah, okay, so that makes sense. We have 3 given languages. Which of the following statements are not true? L1's regular. Nope, that's not true. The third one is not context-free, so C is not true. Wait. Yeah, so B and C are both true. I mean, both not true. Because of this right here. So there's something wrong there. Not sure what. Let L1 be recursive. L2 minus L1 is recursively enumerable. Yep. We don't know anything about this. L2 intersection L1 is recursively enumerable, I think. Oh, no, not necessarily true. I gotta read the questions. L2 union, yeah, so it must be B here. Yeah, because we can't like take the complement of such a language L3. Even number of zeros. Which of the following? Yeah, this is not my strong suit. I really need to get better at this. Even number of ones. Would A work? Um, well, we can't get like. Oh, we can't get like 110 with this one, so this one doesn't work. So B might work. Would C work? Um, oh, this star kills us, so that would give us any number of ones, so this won't work. Yeah, this one doesn't work either because of this string like this. So B has to work, but why does it work? Um, yeah, because this star allows us to go back around. And we can start with the string with a 1 and end with something other than a 1. Yeah, so B would work here. Consider the languages here. Which ones are context-free? Which ones are not? Yeah, all of them are context-free. Because the not equals you can handle with less than or greater than. And then that'll get exactly what you want there. And then for the equals ones, you can just make a rule that, say, like for the 2J one, you can make one for exactly 2 times the number of ones as zeros, and then have another rule which makes exactly one more occurrence of 1. So that's how you would handle that. Let L be any string of length n. Let's just make sure that people aren't complaining about like audio issues or something. Okay, yeah, they're not complaining. Okay, that's a good sign. Any string of length n. Oh yeah, we actually did this one. So the minimum number of states to actually even get W in the first place is n plus 1, and you can always get n plus 1 because it always just depends on like starting the string at a particular spot. So set of all strings of W, well, we can start the substring in any position of W, and then continue after that. And we're only dealing with NFAs here, so you don't have to do the power set construction here. Set of all odd length palindromes, so that's B. Let's see this one. So this one is at least 2 zeros because of these 2 zeros here, so at least 2 zeros. There's a, which of the following is false? Unique minimal DFA? No, that's not the answer. That's not the answer. That's not the answer. Every n non-deterministic VDA can be converted to an equivalent deterministic one. Nope, not true. So that's the answer. If the initial state, so we have an outputting DFA, and for those of you who don't know what that is, if you take a transition, it outputs something on the transition when you take it. If the initial state is A equals 0, B equals 0, what is the minimum length of an input string for which will take the machine from to the state A equals 0, B equals 1, and the output equals 1. Okay, I'm gonna make this a little clearer. So there are 4 possible states. Oops. Circle it back. So let's say that we have 4 possible states. And I'm guessing the start state is this one for all intents and purposes. So I'm going to write 0/1 for input 0, output 1. And then, so that, okay, what am I doing? On input 1, we go to here and output 0. 0, 1 on input 0, we go to 1, 0, 0, I think. I'm not losing my mind yet. And then we can also do 1, 1. Let's do the 1, 1 state. So 0, 1, 0, 0 is a possibility, or it can go to here with 0, 1. And what can 1, 0 do? So 1, 0 goes to 0, 1 potentially on input 0, output 0. And then 1, 0 goes to 0, 1 on 1, 1. Okay, so the minimum number of transitions to take is 3, I think. Yeah, so 3, because we can take this transition, this one, and then this one, and it outputs 1. So the minimum is 3. Intersection of these two languages. Let's see. So the intersection will be these A to the N, B to the N is not going to ever be included. So that's A to the M, B to the M, C. Where M's at least 0, I think. And that's context-free but not regular. Yep. DFA accepts all suits that begin with 0 or 1. No. And with 0, no, because this state. So that's not true. And with 0, 0, yes. Contain the substring 0, 0. Certainly possible, but it doesn't accept 0, 0, 1 for that reason. So that's not true. So C. What about primes? That's not true. Regular but not context-free? Nope. Context-free but not regular? Nope. It's D. Let's be sure of that. Yep. Which of the following are decidable? Whether the intersection of two regular languages is infinite? Yep, that is. Context-free language is regular. Nope, because we can't even get sigma star out of it. Whether two, so accept the same language? Nope. For PDAs, nope, you can't. Whether a given grammar is context-free? I don't think we can. Actually, that's kind of ambiguous because it depends on what it means by grammar. But I would assume that because there are only two answers here for every possibility, this one would have to be true. So I would guess. Okay. If two languages are recursively enumerable, L and L prime, then L is decidable. So it's recursive. False. That's not it. That's not it. Every regular language is context-free. Yeah, so D is the answer. Not every subset of a enumerable set is recursive. Product automaton. Okay, so we can tell that it's going to be 1, 1. P is equal to 1, 1 here because it's the start state here. So then so then 1, 2 will be S. Maybe this is the wrong way to approach it. So we have four states: 1, 1, 1, 2, 2, 1, 2, 2. Where this is the start state. A takes us to the 1 row and 2, so 1, 2. B takes us to 2, 2, I think. 1, 1. So 1, 2 takes us to 1, 1 on A. And then on B, it takes us to 2, 1. 2, 1 on A takes us to 2, 2. On B, it takes us to 1, 2. Oh boy. 2, 2 on A takes us to 2, 1. 2, 2 on B takes us to 1, 1. So it's like a four cycle in some sense. Yeah, so C can't be the answer because there are 3 occurrences of Q here. So there must be 2 of each. So, yeah, C is not the answer. Can... Yeah, so this one can't because these 2 line up, but then these 2 can't be the same as that. So what about these ones? Okay, yeah, so these, it can't be that both of these don't line up. So A has to be the right answer here. And you can check that for yourself. Okay. So 91, Jesus. Every left recursive grammar can be converted to a right recursive grammar and vice versa. Yeah, that's true. 2 is No, it can't, because it may be that the grammar makes the empty string, so that's not possible. The language generated by grammar whose of the form those two is always regular. Yep, and that's pretty easy to show, because if W had a bunch of terminals, you could just make a bunch of rules that generated one of them at a time. Derivation trees are always binary trees because of the form of Chomsky normal form, which is A goes to B, C. So then in the tree, you would have A at the top, B below, and C below it. So it's always a binary tree. So it's 1, 3, and 4. 92. Let's see. Match the following. Palindromes. So H matches with S, so it's not these two. Well, F matches with P, I think. Yeah, because the N here matches the N over here. So the F has to match with P. So it's not this one, it's this one. Sweet. Match the following NFAs with the regular with the regular expressions that they correspond to. I think this is the same thing twice. Okay. Where's the start state? They all have the empty string. Okay, so that doesn't help. Let's see. Where does P go? I mean, we can simplify it. So this one is 0 going here, and 0, 0, star 1. But none of them have that. They're actually almost the same. Where does P go? P could go. 0, 0, 1 star. That's it. Okay, this is not really my best suit. There's no difference between them. I don't think it's really any of them. Yeah, let's see. So what is P? So that is 0, with this state being 0, 0 star 1, 0. There's only a difference in. There's only a difference here, here, and here. Let's see. It's an interesting problem, though. 1, 0 star. Maybe we need to think about this. So P can't match with 3 because it doesn't end up with the same character. So D can't be right. Can P match with 2? No, it doesn't, because let's see. So if it starts with, if it is 2, then that means that it would have a 0, and then skip over the 1, 0 star 1, 0, 0. But then I can go a 0, 1 more time, and oops, and that would give us 3 zeros, but I couldn't get that originally. So A is not the answer either. So P matches with 1. S must match with 4 then. So does Q match with 3? No, it doesn't, because it starts and ends with 0. And so it can't match with 3. So that's not the answer. C is the answer. Jesus, that was a hard one. Or maybe I'm just going insane. Which one of these is regular? That one's regular. That one's not. That one's not. That one is, I think. Yeah, so it's 1 and 4. Let n be an NFA with n states and m be the minimized. Which ones is necessarily true? M is less than or equal to 2 to the n. Yep, and it might not have an except state. So if the final states or in the DFA are changed, which of the following length will be accepted by the new DFA? So these are the ones that end with AB. So it should be this one, I think. Yeah, it's the set of all strings that don't end with AB. Okay, that's good. Following languages. L1 is not a CFL. Nope, that's not true. L1 intersection L2 is empty. Let's see, would that be true? Yeah, because I equals j here, j equals 2 the I here, 2I here, so that can't simultaneously be satisfied because I needs to be at least 0 here, I needs to be at least 1 here. L1's non-regular, and that's true, so that's true. Um, L1 union L2 is, but L2 is, I'm not sure what that's supposed to say. Um, I'm not sure about C and D, but B is definitely true. Well, this one has 5 answers. So we got a CFG here with productions, blah, blah, blah. What is the language of the grammar? So let's see, let's write it out. Or B, A goes to 0A or A0 or 1B. Oops, no, there's just 1. Then B goes to 0B, 0, or S. Oh, no, it's just 1. Okay, so let's see. So B makes 0 to the n, 1, 0 to the 2n. Yep, that's what that is. S is the start variable. So S is this thing union whatever A makes, which is all strings containing 1, 1. I think. So it's not this one. This one has 2 1s in it. Oh, no, it's 2 A's. Okay, never mind. So it's 2. Let's see. So C is definitely not right. It doesn't have to have at least 2 zeros. That's not necessarily true. Could make 2 1s. What about B? I think B option's right. Let's see. Well, certainly this part's right for the B variable. Would the A variable make that part? No. No, that could work. Yeah, I think the B variable, I mean, the B is right. Let's see. Yeah, it should be it should be B, I think. Which of the following languages is not regular? Not that one. The palindromes, yep, that's not regular. Not B. So it's only L2, I think. Finally on 100. Only 140 to go. 100, yeah. Jesus. Which of the following is true? I think they're the same. I guess there could be multiple. Um, We only really need to check C though. Is that complement? Oh, that's really tiny. Yeah, so that one should also be true because if they're the same, then the language intersect the complement of itself is empty, so it must be E. Okay. CFG is given with the following productions. S goes to A. AS. What the world is that? Or A, I think A goes to AAB or BAA or empty. Which of the following strings is generated? So A makes all strings with even. No, that's not true. Well, every string that A can make has an equal number of A's and B's. So it can't make C because it has more B's than A's. Could it make D? Yeah, because it can make a single A at the front. This A matches with this B. This A matches with that B. This A matches with that B because they're always different. Here, they're always different characters. So D, it can make. I don't think you can do it with the other ones because you can't find a. Yeah, you can't find a pairing up like for this one. Yeah, you can't match this A with that A over there. So, and I'm sure the same is true of the B answer. CFGG is given with the following productions. For the correct answer, how many steps were required to derive? So I guess for this past one. How many parse trees are there? Well, there can only be one because you always will generate a character each time. And it's always generating the ones at the front and the end, so you can't actually cheat your way here. And there's only one variable. How many steps were required? Well, we needed 1, 2 to get the A, 3, 4, 5, 6. Yeah, so 6. So it's this one. Membership for which of these is undecidable? Ambiguity is. Finiteness, no. Equivalence for FSA is no. Membership, no. So it's B. Which of the following is true? Every subset, every finite subset of a non-regular set is regular. Yeah, so that's true because every finite language is regular. Minimum state, number of zeros and ones are divisible by 3 and 5, so that means it's divisible by 15, so 15 is the answer. So let's see. The language it's definitely not regular, so it's not that one. It is deterministic context free, so that's not the answer. Is recursive. It's definitely not recursive, so therefore it is a deterministic CFL because it's like zeros and ones again with a character in the middle to help you. Which of the following is regular? Not that one. Okay, so these ones are always kind of tricky. WW reverse will next to each other will get you. So it's not those three, it's C. And it's because you can you can make the W string like one character and the X string as long as you want. Let's see for this one. The language accepted by this automaton is given by the regular expression. Oh, Jesus. So the Q3 state is useless. So is any string that contains an A, it looks like. So it looks like C is the answer for this. Let's just be sure. Yeah, so C is the answer. So it's the same thing. Q3 is useless. Wait, the language accepted is 1, 2, 3, 4? I think they mean the number of states. And yeah, it's a number of states, I think. So we can achieve that with 2 states because as long as it has an A in it somewhere, then we can always accept it at that point. So we can get it with 2 states. Consider the DFA as yours. What language does it recognize? I think. Oh, this is a classic problem. So these are all of the odd length strings because if you have an even length string, you're going to be in one of these 2 states, and if you're odd length, you're going to be in one of those 2 states, and you just flip flop which equivalence class you're in. But it doesn't have that here, so it's not A definitely. Equal number of X and Y, that's definitely not true. Even number. Okay, so this is even plus even, or an odd plus an odd, which is always even. But we want to be in the odd states, so it's D, it's going to be the answer here. Okay, let's just make a quick check, make sure everything is still live. Hope everyone's doing well. Hopefully this video will be of giant use to everyone. It looks like there are some comments at least. Please make PayPal count. Yeah, I will at some point. You can contribute on Patreon. So there's a bunch of links in the description for how to actually contribute, if you want to contribute, but you're never required to do so. Okay, almost halfway. Freaking Jesus. Consider the grammar given below. Which of the strings were generated by it? God, I hate these questions. X goes to XB, or Y, YA. It's hard to parse these too. X or XS, or YA. I think. B goes to Y or YS or YBB. You need to go out? Here, let me open the book. Okay. God, I freaking hate these types of questions. So can one... Well, if one's made, it has to be made with the B rule. So one can't be made because all the B rules start with Y. So this one's not true, that one's not true. 2 can definitely be made then, so we don't have to consider it. We don't have to worry about it. Can 3 be made? So if 3 is made, it would have to be made with the Y rules. So can we make XY from S? Yeah, we can, so 3 can be made, so C is the answer. Good, so that was relatively painless. Go to sleep, baby. My dog is awake. Consider the following grammars. Names have been specified in capital letters. Which of the following statements, let's make sure the stream is still working. Yeah. Which of the following statements is true? So G1, I think, is regular. Let's just be sure. Well, I mean, they're both context-free, but are any of them regular? Well, G2 is not regular. So it's not this one, not that one. So what about G1? Yeah, G1 is regular. So B is true. Well, oh, so here's something that I should pay attention more and you should pay more attention to. These are asking about the grammars themselves, not the languages. So neither of these grammars is a regular grammar because they don't obey the rules of what a regular grammar could be. So actually, both of them are not regular grammars, but they are context-free grammars. Not that. Okay, so 113. Start states. Okay. Okay. This seems massively complicated. I was looking for strings that shouldn't be accepted, but nonetheless are. Well, both of them accept AA. So this one won't work. This one won't work. And this one won't work. So A is the answer. Sometimes it's just a matter of eliminating choices, even though it's a massively complicated problem. Consider the regular expression whatever. What DFA accepts this? Well, A is not. Well, these are not deterministic automata for sure. So the question is wrong to start with. What else can we say? Okay, yeah. So it is A, because in order to take this transition, we must have ended with an A to get to S1 in the first place in order to go to S3. Similar thing for S2. If I want to take that transition, I must have ended with a B. So that means I read something and then ended with AA, then BB, which took us to S3. So that one's that. More of these. I hate these. Which of these? Well, these two don't have final states, so that doesn't really help. Maybe it was just an error, and all of them were final. They're missing transitions too. I'd rather not do it and worry about it. Which of the following regular expressions? Why? We already have a regular expression for it. Let's see. Well, this one won't work, so this one's not right because of the plus at the end. Same thing for this one, won't work. This one won't work because it doesn't have an A, or a B, B in here, I don't think. Oh, wait, no, it can. Never mind. That's not right. Oh, we need to have this choice right here, I think. And this one would require us to go around again in order to get that second choice, which I think there must be some string that doesn't work. So I'm gonna go with C on that one. Okay. Let ds denote the decimal value of s. Let d all of them. Its modulo 5 is 2 and modulo 7 is not 4. Which of those following statements is true? It's regular, I'm pretty sure. Yeah, because what you can do is just look at all the possible cases of what could happen and then make the product DFA for the whole thing. Let the number of zeros in S, number of ones in S, which is A is regular, I'm pretty sure, so that's not the answer because 3-digit primes, there's only a finite number of them, so it's a finite language. The number of zeros and ones differs by at most 2 for every prefix. No, that is regular because you can just keep track of the last two. If the difference ever becomes 3 or more, then you can actually go to a state afterward. It's because this difference is bounded. This is not regular because this one says about prefixes, but this one can be anywhere in the string. This one just corresponds to setting some of the states final, and some of the other ones not. So this one is regular. I mean, not regular. Which of these is not context-free? L1 is context-free. L3 isn't, I don't think. So L3 I'm gonna pick. What about L2? Yeah, so that one's also not context-free because you can just, because the counts don't have to line up here. Like this range is not the sum of these two. Like for this one, it was the number of zeros here is the number of ones plus the number of zeros here. So I'm going to go with L2 and L3 on that one. What is the length of the derivation to generate the string? There isn't a grammar in the above question. Well, Yeah, so there isn't a grammar there, so I'm not going to do it. Which is maybe it was this one. Which of the grammars makes this? So this one I'm pretty sure doesn't. This one doesn't because this needs an A and a B here. So I think D is the right answer, and this one doesn't because of the same reason. So then what is the length? So D is the answer to that one. What about this one above? Well, we need one to, for the S rule, we need one to take C out. We need the maximum to, yeah, because each of these rules will make one of each character, and for whatever the larger one is, we need the rest of them to be generated by the other A or the B variable. So it would be max plus 2 because because we need one for this preliminary rule and then one more for S going to empty. So it's this one, A and that one. We actually did this one. So this one was actually a really, really interesting problem, and I would highly recommend that you do it yourself. I'm going to skip over it here. But 9 is the minimum. It may seem weird. Why is it 9? But it's actually really interesting. So I encourage you to do it. L1's regular, L2 is deterministic, context-free, L3 is enumerable, not decidable, not recursive. Which L1, L2 is deterministic. Yep. So that's false. Well, it's a true statement, but it's not the answer. L3 intersection 1 is recursive. No, that's not necessarily. So that is false. So I'm going to go with that one. Which of the following statements is correct about this grammar? So is it ambiguous? So can we make a string in multiple ways? Yes, we can make the empty string in multiple ways, so that's true. Produces all strings with an equal number of A's and B's. No, it doesn't ever make us. You can't make a string with a lot of A's in a row, I don't think. So I don't think that's true. Yeah. Can be accepted by a deterministic PDA. Yes. I think. Yeah, it can. So it's a good exercise to think about why it can. But yeah, it can be. So we have automaton. T is the only final state. Consider the strings, those three. Oh, okay, this is just easy. So does it accept U? So A, A, sorry, A, B, B, A, B, A. So U says yes. B, does it say yes? B, A, B, nope. And then W, A, B, B, nope. So U, so it should be D, I think. Which of the following strings is not generated by this grammar? Yeah, be odd length. Even length palindromes. Oh no. Yes, it actually gets all palindromes. So B is the only thing that's not a palindrome. So therefore, that's B. Which this describes the So this one's pretty easy. It's A because this is A B star. A plus B, B, and there's nothing else after that. Consider the regular grammar. My Hill in the Road equivalence classes. Oh boy. This is not something that I am well versed in. So let's see. Let's actually just write out the grammar as is. Well, this is a regular grammar. So let's see. Let's actually just make the automaton for this. So B, A, S can go to empty. Just making the transitions in the usual construction. So to convert this to a DFA, it'd be, let's just call this QF. So SQF is the start state. On input A, we would go to A. On input B, we are here. On input A, we go here. On input B, we stay here. And that's the final state. So there are two equivalence classes about even numbers of A's. Yeah, so it only has to do with the A's. So even and odd, I think. And that's only about the A. So I think A is the right answer here. A. Which of the following statements is not true? Every language has a regular superset. Yes, that's true. Because sigma star is a regular superset, so it's not that. Every regular language is a regular subset. That's the empty set. Every subset of a regular language is regular. Nope, that's not true. So C is the answer. Every subset of a finite language is regular. Yes, because it's always finite. Which of the following languages is accepted by a non-deterministic PDA but not deterministic one? So this one is not accepted by either. This one is accepted by a DPDA. This one's regular, so it's accepted by both. So it must be B, and because it's part of one of the complements of ADN, BDN, CDN, which is used to show that these two models are not the same. Easy. It'll be a context-free language. Then the language is always a context-free language. So that one's easy. Consider a PDA that... Oh boy, Jesus. Z0 is the bottom of stack set of states where S and F are the start and final state, except by final state. Transitions are depicted in standard manner. Top is X, then it can be read B from the input and move to state T after popping and pushing the symbols Z0 and X in that order, blah, 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 blah. Well, there isn't a PDA below, so I can't really answer the question, sadly. In the context-free grammar below, S is the start symbol. Let's see. S goes to A, S, A, B, or empty. A goes to B, A, or empty. So A will make B star. So it's not A star, B star. So it's not that. The number of B's and A's has nothing to do with each other, so it's not that one. Yeah, so it must be this one, because the B's are only generated in this part, so that means that we're recursing here, and there's only A's on this part. And every A matches with one B, and there could actually be more B's. So B is the right answer. And since the A's have to be at the front, this one won't work because this star will actually kill us there. Okay, state machine. With the following state diagram for the next state S plus in terms of the current state and the input variables X and Y is... I have no idea what this notation is. Uh... So let's see, if we were in 0, so S, so we could either be in 0 or 1, but the X and the Y variables can also be 0 or 1. Okay, yeah, I'm not sure how to answer this one. Maybe one of you can provide me in the right direction for this type of problem. Okay, let's just make sure the stream is still up. I don't know how I'm still up. Okay, let L be a regular language. Consider the constructions below on L below. Repeat. So which one would lead to the non-regular language? So repeat can. So 1 can. 2 and 3 can't. Because we've done those in an earlier question. Half. It turns... Yeah, it turns out you can show that half of L is regular, so it's only 1 here. I might do that in a future video because it's actually quite complicated, but half of L, where L is a regular language, is regular. Let L be regular language. I think there's something screwy happening there. Yeah, it looks like there's something screwy there. A finite state machine which takes as input a binary number from the least significant bit, which is following as true. It computes... What does it do? So it skips over the zeros. When it sees a 1, then it complements the bits. So it does 2 complement, because the 1's first, and it complements all the other bits. Yeah, since 2's complement. L1 is deterministic, no. CFL, no. L2 is deterministic, CFL, yes. L3 is a CFL, nope. It's not even a CFL. L3 is not even a CFL, so B is the answer. Let's just be sure. Yep. A is false, because it's not even context-free, so that's easy. Let L1 be recursive, and L2 be recursively enumerable. So that was not true. L1's bar's recursive. Is that one true? Yeah. These are not true. L2 bar is not recursive necessarily, so it's B. So we're looking at languages between NFAs and PDAs versus DFAs and DPDAs. That's an interesting idea. DF subset of NF, nope. A strict subset, I mean. So these two are not true. And this one's true, this one's not true, because DPDAs are not the same thing as non-deterministic PDAs. So the last one's true. Let's do. Got a machine M here. The language recognized by M is... So we can forget about this state. So it must end in ABB, I think. Or it contains this... No, it ends with two B's. Wait. So it doesn't necessarily have to end with ABB because it can have like three B's at the end here. So that's not it. This is not true because it could do A, B, A like that, and it doesn't have A in it. Every A is followed by exactly two B's. No, that's not true. Followed by at least two B's. Yeah, that's true, because we have this self loop here. P is decidable and P is 2 is undecidable. So if P1 is reducible to P3, that doesn't tell us anything about P3. P3 is undecidable. Yeah, that doesn't tell us anything. If it reduces to an undecidable problem, that doesn't tell us anything. P3 is undecidable if P2 is reducible to P3. That is true, yes. So C is the answer there. Let L... Yeah, so the order matters on reducibility. Let L be a regular language, M is context-free. Both of the alphabet sigma complements, which of the following about their union of the complements is true. It's not regular or context-free necessarily. So it should be none. Yep. Which is true about the irregular expression. Finite set, nope. Infinite set, yes. Of finite strings. There's no such thing as an infinite string to start with, so B is the answer there. This language is regular because of this upper bound on the size. So it's a finite language, and therefore it's regular. Even though it corresponds to a non-regular language, but that is in the case where n can be as big as you want, where here is the maximum. Which of the following expressions is equivalent to a X or B, X or C? So what I remember is that A XOR B is the same thing as A complement B plus A B complement. So A bar B plus A B bar XOR C is the same thing as saying okay, this is getting complicated. I know there's going to be an A times B times C here, and it's not going to factor, so it can't be these two. I mean, we could make a truth table, but this is not something that I know about much. Let's take this thing, complement C plus A, B, this thing C complement. Yeah, I'm going to skip that one because that's not something that I am familiar with. Although it's a long time ago, so maybe they got rid of this in future gates, and we haven't encountered it yet. Um, Consider the NFA shown in the figure. X is the start state. Let the language accepted by with Y is the only final state, so let's mark that as final. BL1. Oh, okay. So if we made Y the only final state versus Z being the final state, what is the relationship between those two languages? They can't be the same. Can they? Correction in question. There's an edge from Z to Y labeled 0. Okay. And from Y to Z labeled 1. In place of double arrowed or no arrowed edges. Oh, Y and Z are the same state in some sense. Yeah, yeah. Because their outputs go to the same place. Yeah, so they're the same language. Okay, so that's pretty good. Let P be an NPDA with exactly one state and exactly one symbol in the stack alphabet. State Q is both the starting as well as the accepting state. It would have to be. The stack is initialized. Uh, let LP be the language. Let NP be the language accepted by the P. LP. Reading the string and emptying its stack, which is a. Oh, this is actually interesting. Yeah, because we could leave transitions out, so it doesn't. Neither of them have to be sigma star. Okay. Yeah, yeah, because we can leave both of the transitions out if we wanted to. Consider regular grammar. S is what is the minimum number of states? So S goes to XA or Y. So how many variables are there? 1, 2, 3, 4. I think we can. Can we do 4? Or maybe we can do better. I'm not sure. Let's see. C goes to SA or empty. Y goes to WA. W goes to SA. So S, let's say S is the starting one. X, Y, Z, W. XA, YA. X goes to ZA. Z goes to SA or empty. Y goes to WA. W goes to SA. Oh, so the Y state and the W state are completely irrelevant here. Okay, that's nice. Oh, no, wait. What am I saying? Of course they're relevant. What am I doing? um, did I do that right? Let's see. Um, what's the minimum number of states? Oh, the y and the w path can be removed because it's essentially equivalent to the other path. Okay, yeah, yeah. So we can get away with 3 states. Yeah, that's right. A language satisfies the pumping lemma. It also satisfies the pumping lemma for CFLs. Then what does satisfies the pumping lemma mean? If it means satisfies the entire thing, then it has to be regular. But if it satisfies the conditions, it's just the last 3 conditions for both of them, then it's neither necessarily. Because you can have languages that satisfy the conditions but are not regular or context free. So we have a CFG here. Which of the following non-terminal strings has more than one parse tree when parsed with this grammar? So I think it's not the first one. Oh, no. It must be the first one because it's the same operator multiple times. So we could do the plus starting at the end or at the beginning. So it's A in this case. Okay. It's just asking for whether this grammar is ambiguous and showing which string shows that it's ambiguous. We have a grammar here where E is the start symbol. For a terminal string, how many parse trees are possible? Well, we can have the plus go out in the middle, or here, or here. Or we can go right, or we can go left. Okay, yeah. So it must be 5 in there. A sync in a directed... I'm not sure why we're talking about directed graphs now. Following algorithm describes how to do that, blah, blah, blah. Choose correct expressions for E1 and E2. Oh, okay. It would be... So E1, while there is no edge there, so it can't be these two. And the last one is... E2. So if j is less than or equal to n, I is set equal to j. Yeah, I've set equal to j, yeah. It's just updating the index I as you're going along. Yeah, okay, that makes sense. Correct expression for E3. Now, this is awful code. If j is not equal to I, and I think it must be one of the 2 OR conditions for it to even make sense in the first place. Well, we're looking for a sync, so there must be no way back out. So there must be a way in and not a way out. So that one must be true. Not sure why these are showing up here. Each node contains a route to next hop router. Node Identify the correct table. Okay, yeah, these are not in my wheelhouse for this. Let's skip over them. Following finite state machine accepts all binary strings are respectively divisible by 3. Number of ones is divisible by 3 and 2. So I think this should be a. Let's just think. Yeah, because of the zeros cyclically go around the rows and the ones cyclically go around the columns. So it's A in this case. So this one is not regular. It is context free. Yeah, but not regular. L1 is a recursively enumerable language. An algorithm enumerates all the words in it. Define another language as so like a string with a later string that is produced. So L1 recursive. So if we can solve L1, can we solve L2? Yeah, because we can just enumerate strings in pairs. So this one is true. We can just operate in parallel until the solver for L1 says yes. Even if it was enumerable, it would still work to show that L1's enumerable. L2 recursive. Yeah, because L1's a recursively enumerable language. Yeah, that one's also true because it just prints the words. Yeah, so that one's also true. So both of them are true. Which of the following regular expressions is not equivalent to this? Let's see. Okay. Yeah, we can't make the single character A or even B with this one right here. So this one's the answer. We can't make those two, but we can with the other three because the B stars decouple from the A part. There exist CFLs such that all of the CFGs generated them are ambiguous. That's true. So the answer is that's not the answer. Unambiguous CFG always has a unique parse tree for each string in the language generated by it. So that's true, but that's not the answer. Both, yeah. So that one's not the answer. We've seen that multiple times. God, I hate like really formal notation because you can't visualize it. K is the set of states. F is the final states. Let's see. So this machine looks like this. So we have A epsilon goes to A. B epsilon goes to A. A epsilon goes to epsilon, it looks like. Then F self loops on everything. Yeah, A goes to epsilon. B, A goes to epsilon. So which string is not in there? Well, the triple A's will get us there. Will BAB get us there? Yeah, so that'll get us there. B, A, B, BA, yeah, that'll get us there. So why does this one not go? So A, B, A, B. So that last B must be over there in the F state. A, B. I must have copied it wrong. So you push an A for every occurrence of A and B. So the contents of the first half yeah, I'm not sure if this is right. Unless there's something. Which is not. Oh, maybe the condition you have to accept by empty stack. At which point, yeah, B would not be the answer because the middle character would have to be the one in the middle. Okay, maybe there's some notion of accepting by empty stack that they picked here. Okay, yeah, here's a fun one. Consider a language that's 0, 1 star or empty set. Otherwise, which of the following conditions is true? L is recursive, and the reason is that a decider actually does exist. It's one of these two. It's just I don't know which one it is, but it exists. That's the key. It trips people up, but it's just the fact that it exists for that language L that's what actually matters. The regular expression is the same set as yeah, I think it's A. Yeah, I think it'd be, yeah, because you can just interchange the role of 0, 1, 1 here in this particular case. I think you can change the order there. If the strings can be enumerated in a lexicographic order, which of the following statements is true? Could be finite, could be regular, not finite. It could be any of them actually. Yeah. So it's the biggest option here. You can always enumerate the strings in any order. In lexicographic order, at least you can enumerate them. Consider DFAM, S 7-bit binary strings of which the first, fourth, and the last bits are 1. The number of strings that are accepted by M is... So if the first bit is 1, if it was 0, 0, 1, then no matter what goes here, that's accepted. So that gives us 4. If we had 1, 0, 1, 1, the only way we can get to a final state is 0, 0, 1, so that gets us 1. If we had 1, 1, 0, 1, then the only way we can get to the final state is 0, 0, 1, so that gets us another 1. Then we have to have 1, 1, 1, 1, and then 0, 0, 1 only gets us there, so it must be 7. So that's pretty cool. So S goes to ASB or SS or empty. It is ambiguous because the empty string. There exists no, that's not true because of this condition, so that's not true. Um, there's no DFA for this, so that's not true. So it must be this one. There's a DPDA for it. And let's see, so why would that be? It's I know it's the same number of A's and B's, so I know you can make a DPDA for that for sure. So, but it's not all of those strings. That's worth thinking about though. Let be a polynomial time computable by bijection. Let the inverse be computable, which cannot be true. So it's just a computable function. We don't know if that's true or not. So that can't be true. Can't be the answer. Can't be the answer. Oh, C can't be the answer because you can't reduce from an undecidable problem to a decidable one. Single tape Turing machine has two states. Tape of the alphabet is one. Blah 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 blah. The entry. Which of the following statements is true? So let's see. So let's actually draw this out. So let's just say is Q0 the start state? So it goes on input 0, writes a 1, moves right. On input 1, it does almost the same thing. And blank, it goes to a halt state. Q1 will stay there. And 0, oops, getting my notations mixed up. Then here it goes to 1, 1 left, and then blank, blank, blank left. Let's fix that. So that's blank goes to left. So it's converting everything to, it converts the first character to a 1 no matter what, if it's not blank. So it does halt on the empty string, so that's not true. At least I don't think so. Oh, I didn't see the plus. I thought it said star. So B is not right for sure. M halts on all strings ending in a 0. Okay, let's see. So it converts the first character to a 1. Then, as long as it sees zeros, it moves right. When it sees a 1, it goes left. So it's converting everything to a 1. Yeah. It won't halt on anything because it's converting everything to a 1 and then just going back and forth across the tape. So it won't halt on any string. Good. This is taking forever. MWI is a triplet whose first component, Turing machine, is a bit. Um, M halts on W. So A is recursively enumerable, and B is not. The does not property is not recursively enumerable. So the 0 and 1 doesn't really mean anything. So A is the answer here. Got an NFA here. Changing the accept state to a non-accept state. Let L1 be the... Which of the following statements is true? Yeah. So if we change the final state, so this one's just a normal state, this one's final, well here, we can get the empty string by just staying here, and any other string by just going over here and looping here. So in fact, it's 0, 1 star. The language accepted by a PDA, which is stack is limited to 10 items, is regular. Yep. Finite state machine. A is the starting state where arc label XY 1-bit input, 2-bit output. Let's see. Outputs the sum of the present and previous two input. So if it sees a 0, it goes back to A. When it sees a 1, it progressively moves through the machine. Oh, okay, yeah, it is A. Because, yeah. Because it's keeping track of like what the present and the previous. Yeah, so it's the sum. So it'd be worth actually to dive deeper into that, but convince yourself that it is correct. The smallest finite automaton, length divisible by 3. So this one is pretty easy. This is 3 states. Complement of a recursive language is recursive. Yep, so that's A. C language is not context-free. It's not regular. Not parsable by only a Turing machine, I don't think. I think it's context sensitive. Okay, I'm not sure what this is doing. And the context sensitive part is because of all the template stuff that it, no, not template, all of the headers that it has to do. Because it being able to with all like the macros and stuff, that it really depends on the context in which it is placed. So, and also like the number of the functions and whatnot. Require a 4-state automaton to recognize the regular expression. No possible answers given there. Let S&T be a language represented by those regular expressions. Which of them is true? So certainly S is a subset of T, but are they equal? Yeah, I think they're equal. Yeah, because the B star here can be replaced by just going around this one as many times as you want, so they're the same. Which is so we got a grammar here. Not sure what this notation is. Okay, yeah, so it's only making... Oh, okay, I see what this is doing. So this is 0s0 or 00. So this is all even length strings. So this is regular, but it's not 0 plus because it doesn't have the empty string. Okay, that makes sense. What can be said about a regular language? Let's just check to make sure the stream is still alive, which I'm sure it is, but let's just be sure. Oops, clicked the wrong button. So we're still alive. What can be said about a regular language whose minimal finite state automaton has two states? I think we did this one in office hours. It was D in this case. And we were able to show that this question is actually wrong. This, you can also get the empty string. So the fact is that it doesn't say deterministic here. So if it said deterministic, then you can actually get more. If it was non-deterministic, you can still get the empty string, set containing the empty string. Does a given finite state machine accept a given string as a decision problem? Yeah, so that's decidable. Does it, given context-free grammar, generate an infinite number of strings? That's also decidable. So both of them are decidable here. Construct a minimum. Okay, so this one doesn't have an answer to it. Neither does this one. But if you have questions, feel free to drop them below, and we can certainly go over those. I'd rather just do the multiple choice ones because that's what the GATE exam is more suited to lately, at least. Okay, that posture. All right, consider the regular expression 0 plus 1 n times. Minimum finite state automaton recognized by this has n plus 1 states. And the reason for this is that you can just do 0, 1 n times. And yeah, so you can get n plus 1. It doesn't say that you have to have a deterministic machine here. So you can get away with n plus 1 because there's no other transitions. And you can't do better than this because if you had any other transition that went somewhere else, then you would get more strings than what you actually wanted. Context-free languages are closed under... It's the first time I think this was asked. Interesting. So union intersection, nope. Union cleaning closure, yeah. So it's that one. Let LD be the set of all languages accepted by PD by final state, empty stack, and these two are the same. Because you can show that if you had a bunch of final states here, you epsilon, triple epsilon your way to a state that pops everything. That's a final state. Neither of these two is no longer final. So that's how you do that. If L is a context-free language and L2 is regular, which of the following is true or false? Complement of L2 is regular, so that's not false. L1 bar is context-free, so that counts. L1 intersection, so L1 minus L2, remember, is equal to L1 intersection, the complement of L2. And this thing, context-free intersection regular, is always context-free. So A is in there, so the answer is E. The grammar that is both left and right recursive for a non-terminal is whether it's ambiguous or not. You can't determine anything from it necessarily, because that's not what ambiguous refers to. And in fact, you can always split any rule into left and right recursive. or at least for some languages you can always do that. If the regular set A is represented by this and B is this, which of the following is true? Um, okay, yeah, they must be the same because if you think about it, 0 must be followed by a 1. So you can think of this the first language as a bunch of 1s, and then a 0 with a 1 after it, and then 1, 0 with a 1 after it, etc. And the same thing is true here. If you have a 0, this 1 will get you, and then that 1 will have some number of 1s after it before you see a 0, but then you must have a 1 again. So, yeah, so these two are the same. Which of the following sets can be recognized by a DFA? I'm not sure what these under ellipsis means. Number zeros equals number ones, that's not possible. The set, no, because this is like 1 to the n, 0, 1 to the n. Kinda, not quite, but it's almost like that. It can't do unary because that's just a bunch of ones or whatever. Binary, this is just 1 with a bunch, any number of zeros after it. So that's 1, 0 star, so A is the answer there. Power recognition of languages, which ones are non-deterministic NFAs are equivalent to DFA, so that's not the answer. So we've seen this one, so B is the... Oh no, this... Oh, I didn't check the other one. Oops. Non-deterministic Turing machines are equivalent to DPDAs. That's also not true. I mean, it's false. So the answer is okay. So it must be D. Yeah. So remember to always read all of the answers, which is something that I haven't been doing this during this video, but oh well. The string 1101 does not belong to which of these sets? So it belongs to the first one, so it's not that one. So B it belongs to because of this one and then the 101 over here. Both C and D, well, the answer is D. Let's see, does it belong to C? 1, 1. So the 1, 1 would have to be generated over here, but the 0, 1 is back over here and you can't backtrack. So C is the only real answer there. There's no D answer. How many substrings of different lengths can be found from the character of length n? So let's say we have a string W1 up to Wn. How many strings, different lengths, non-zero can be found using a character string from it? So that means we start the substring at index I and then go to index j. So the number of choices is n minus 1 for the choice of I. And then, let's see, how many do we have? Oh, no, we have more, because the I could be over here. So in fact, we have n times n plus 1 over 2. Because we're really just thinking about splitting the string into 2 pieces. So it's really just n choose 2, which is what this is. We're just splitting the string into 2 possible pieces. Let L be the all binary strings where the last 2 symbols are the same. The minimum number of states in a DFA accepting L is what? So that means... Oh, so let's see. Deterministic finite 0 state? I'm not sure what that means. But that maybe means NFA. So let's try. So if we had something like this, then we need to have a different path here, because if I join the path, then I would accept 1, 0 here, which is not allowed. So I would need... Oh, maybe... Oh, it does say deterministic. Okay, I didn't see that. So what's a DFA for this? So let's call this Q0, Q1, Q2, Q3. So Q0 on input 0 will go to Q0, Q1. Then on input 0, it will get to Q0, Q1, Q3. And then it'll stay there. Yeah, it'll stay there on 0. On 1, it would go to Q0, Q2. And for the same reason, on 1, it'll go to Q0, Q2, Q3. On 0 from Q0, Q2, it'll go to over here. And on 0 from 0 to... So the 1 will stay here for sure. On 0, it'll go back over to here. And on 1, it'll go over here. And on 1, it'll go over here. Yeah, so you can get it on 5 states. Oh, I forgot to circle that one. Every finite... Which of these is false? Every finite subset of a non-regular set is regular, so that's true, so that's not the answer. Every subset of a regular set is regular, that is not true, so the answer is B. Okay, which of the following sets is not countable? Set of all strings over sigma, that is countable, so it's not the answer. Set of all languages, that is uncountable, so it's B. Which of the following regular expressions denotes the set of all strings not containing 1, 0, 0 as a substring? 1, 0. So it's not A, because you can just go around the star as many times as you want. 1, 0. So it's not D either. C can get it, so I think it's B. Oh, I'm thinking 101. Oops. Oh, I'm a dummy. 1, 0, 0. So can B generate one? Yeah, the 1, 0 here. So that can make 1, 0, 0. Can C make it? No, it doesn't make the string 1, so no 1 here. So that doesn't work, so D is the answer there. Maybe a succinct explanation for that would be nice to have. Which of the following is not decidable? Equivalence of 2 given Turing machines, that is not decidable. So B is the answer there. So this one can be done by brute force. This one can be certainly done because you can just search the DFA for a final state from the start one. And this one is kind of similar to that. Which of the following languages is accepted by DPDAs? So this one is, because we've seen that like 4 times already in these questions. Which of the 2 following 4 regular expressions is equivalent? I think 1 and 4 are. No, they're not. Never mind. So 3 is not equivalent to either, I don't think. Oh, wait, no. This is relating to a question we had earlier, like where we had any even number plus 1 or 0 gives us any number. So 2 is not equivalent to any one of them because it's not equivalent to 3, it's not equivalent to 4, it's not equivalent to 1 because of the empty string, and actually the 0 gets us there. So 2 is not considerable. 4 is not considerable again because of the empty string, so it's not 4, so the answer is 1 and 3. And the reason is that any number is either an even number or an even number plus 1. So get an even number, any number you want, plus 0 or plus 1. So that's pretty nice. Which of the following statements is false? Halting problem is undecidable. That's true, so the answer is not that. Determining whether is bail. Just deciding whether CFG is ambiguous is undecidable. That's true, so the answer is not that. Given it is undecidable whether they're the same language, so it's probably the last one. It's undecidable whether two regular grammars have the same language. But it is decidable to do that because you can convert them to DFAs. Let L be a language. L has an equal number of A's and B's is regular. Nope. A to the n, B to the n is regular. Nope. X has more A's and B's is regular. Nope. D is certainly regular because the counts of the A's and B's have nothing to do with each other. If L1 and L2 are CFLs and R's regular set, one of the languages below is not necessarily a context-free language. L1 intersection L2. Yeah, I was blanking out. Yeah, because it's the intersection of context-free languages. Define a context-free language set of prefixes, and L has an equal number of zeros and ones. I don't think we can. Then the prefixes can be anything. Yeah, it can be anything. So it must be B here, because you could have an equal number of zeros and ones at the front, and it could be anything at the front. The grammar whose productions are this is ambiguous because so I don't think it's A because it needs to mention parse trees to start with. And there are only two parse trees of that sentence because there's only two ways that we could apply the next rule once we go down one level. So it can't be C. It definitely is not A. I'm not sure what top means. Yeah, I'm not sure. I'm gonna give it a go, and I think D is the answer there, but I'm not sure what the correct way of saying B is. We've got a sequential machine. The number of states in the minimized machine will be so I'm not sure what this notation is. Well, actually, we can notice that B and C are very similar to each other, that they produce the same thing. Okay, so we can merge those. Can we merge any others? No, because they're fundamentally different in at least one way. So I think we can only do 3. We had 4 states to start with, so we can only merge 1. In some programming languages, an identifier is permitted to be a letter followed by any number of digits or letters. If L and D denotes a set of letters and digits respectively, permitted to have any, so it should be L followed by L union D star, so it should be B. Consider a grammar with the following productions. Those things. The above grammar is Oh, I've never dealt with context-sensitive grammars. Oh, so it must be a context-sensitive grammar. I'm not sure about LRK. That's not my strong suit, so I'm not going to deal with it. Which of the following definitions below generates the same language as L, where we have XEN, LADZN. So 1 works, 3 does not work. XY or I don't think 2 works. Yeah, because the pluses here don't have anything to do with each other necessarily, so it's only 1. A finite state machine has the following state table, then put it. If the initial state, so what's the shortest input sequence to reach the final state? So we must reach either B or D. So if we're in A, zero one will get us there. If we're in B, 0, 1. Yeah, so 0, 1 won't work. Will 1, 0 work? So the state A works, B, 1 input, 1, 0. 1. Yeah, that'll take us to C. Will C take us there? 1, it takes us to B, and D takes us to B, which takes us to C. So B is the answer there. L union R and R are respective. So L union R is just sigma star, so it's always regular. And R itself is not regular, so it's C here. Okay. Which of the following conversions is not possible? Regular grammar to context-free grammar? No. Non-deterministic PDA to deterministic PDA? Yep, that's not possible. Which of the following features cannot be captured by context-free grammars? Variable names of arbitrary length? No. Or at least I don't think so. Whether variables declare... Yeah, so it's not sensitive to the context in which the variable is declared to the grammar. The regular expression for the language recognized by this, well, we can see that it's 0 star, and if it has a 1, it can do any number of 1s, but it can't have a 0 afterwards. So it must have some number of 0s at the front, and then 1s if it wants to, but then no 0s after it. So it is 0 star, 1 star. But there are other regexes you could make there. Every subset of a countable set is countable. That is true. Yeah. That's good. If a state machine described in a figure should have a stable state, I'm not sure what that means. The restriction on the inputs is given by... Okay, I'm not sure what that means. Which of the problems is not NP hard? Actually, we don't know that. So all of these are in P, but we don't know if P is not equal to NP, so we can't actually conclude anything about that problem. Follow A is a set of terminals that can appear immediately to the right of a non-terminal A in some sequential form. We define 2 follow sets, the 2 sets. I think they mean R follow here. I'm not sure what this is actually saying. I'm not going to answer that. Which of the following regular expression identities are true? Let's see. Oh, okay, I see. There's no star attached onto here. So this one doesn't work. This is everything. This is not everything. Yeah, these are not the same because this can have R's and S's. This can't. So this one's the right answer. If G is a context-free graph and W is a string of length L and G, how long is the derivation in L, assuming G is in Chomsky normal form? This is 2L minus 1. But that's not necessarily true if you have the empty string, but that's just a small case. Context-free languages are closed under union and clean enclosure. So that's A and D, so that's E. Hopefully I can finish this pretty soon. Which of the cases stated below is the following statement true? For every non-deterministic machine, there's an equivalent deterministic one. That one's true. Not for PDAs. It is for Turing machines. Okay, I'm not sure why that's there. So E is true. Consider the following two statements. Which of the following statements is correct? S1 is regular. Good. S2 is not regular. So only S1 is correct. So A is the answer there. Which of the following statements is true? If a language is context-free, it can always be accepted by a deterministic. Nope, that's not true. The unity of context-free languages is context-free, so that's B. For given an arbitrary NFA with n states, the maximum number of states and equivalent minimized DFA is at least to the end. Consider a DFA over AB, accepting all strings which have a number of A's divisible by 6 and number of B's divisible by 8. What is the number of states? I think that should be 48. Yeah, it should be 48. We answered a question earlier about that. Consider the following languages. Which of these is regular? The I squared one, that's perfect squares, that's not regular, so it's not that one. 2I times I, that's just even length string, so that's okay. WW reverse, that's not regular. WW, that's not. So it should only be L3, and it is. So D. Consider the following. Given a Turing machine over the input alphabet sigma, any state Q of M, will the machine ever visit state Q? So this is undecidable because we can just basically decide the halting problem based off of this. But it is partially decidable because you can just simulate the machine. So that's true. Construct DFAs for the following languages. Maybe we can do this one. So BAAB. So the idea here is we make the automaton for BAAB, just make it straight away, and then AB. And then for the other transitions, we just fill them in as necessary. So like here, this one will be a B. This one on B will come back here because we just saw B. Maybe that's the start of the BAAB sequence. Then on input A, this needs to come all the way back here. Oops. This needs to come all the way back here. Because that just basically just ruined the whole sequence. And then for an odd number of A's and an odd number of B's. So that means we will have to make 4 states: Q, EA, EB, which denotes even A, even B, even A, odd B, odd A, even B, odd A, odd B. So that's the only final state. That's the start state because the empty string has 0 of both. So B's go across and A's go up and down. So that's how you do that. Give a deterministic PDA for this one. I'm not going to do that, but it's pretty simple to do. Because what you do is you just basically just make the machine for A to the N, B to the N, make the one transition in the middle reading a C, and then all the other, and then the one that reads the B and pops off the A. Actually, for the A's, you need to push on 2 characters instead of 1. And then for the B part, you need to read off of the input twice, which means popping off twice. So, but there are other ways you could do it. Okay, we have a decision problem here. Does M loop forever on W? Show that X is undecidable. I'm not going to do that here for interest of time. I already spent a lot of time doing this anyway. Choose the correct alternatives. Let R be that regex, S be that regex, T be that regex. Which of the following is true? So S is a subset of R. That's true. So B is not true. S is a subset of T. Yeah, so S is a subset of T, so that's not that one. S is a subset of R. Well, these two answers are the same. Okay, so that's the answer there. 235. We're closing in. Choose the correct alternatives. Which of the following can be the strongest statement about a finite language? It could be undecidable. No. It is a regular language, context sensitive, and Turing machine recognizable. So it's B, C. Oh, the strongest one. Okay. So the only one that would be is regular. I mean, it's stronger to say all 3, but oh well. Choose the correct alternatives. Recursive languages are a proper superset of context free. Yep. Always recognizable by... Nope. Type 0 languages. No. Recognizable by Turing machines, yeah. So A and D. Choose the correct alternative. It is undecidable whether our arbitrary machine halts after 100 steps. No. Turing machine prints a specific letter. Yeah, that's undecidable. You can use the halting problem for that. A Turing machine computes the products of 2 numbers. Yeah, that's just deciding the behavior of it. So it's B and C again. Not again, it's the bottom answer again. Choose the correct alternatives. Let R1 and R2 be regular sets defined. Then, so this one's not true. This one is true. This one is true. That one's not true, so B and C. Context-free languages are both closed under union, non-intersection, concat, and not complement. Regular are closed under all 4, but context-free are not. Which of the following problems are decidable? Membership problems in context-free languages. Yep. Whether a context-free language is regular. Nope, we've answered that already. Whether FSA halts on all inputs. It always does, so that's true. Membership problem for type 0, nope, that's not decidable, because that's just Turing machines. So A and C. Regularity is preserved under the operation of string reversal. Yes. They probably mean language reversal, but yeah. All subsets of regular sets of regular, no. We've answered that already. A minimal DFA that is equivalent to NF always has to the end states. No, that's not always true. The intersection of two CFLs is always a CFL. No, we already saw that. A is recursive if both A and its complement are accepted by Turing machines. That is true. That's a theorem that we proved in that class, and the idea is that you simulate one machine and the other one in parallel. One of the two will accept at some point, because it's either in the complement or the original language. So one of the two machines will stop at some point. So you just simulate them in parallel in lockstep, and at some point one of them will say accept, and then you can decide what to do from there. The context-free grammar is ambiguous if the grammar contains useless non-terminals. No. It produces more than one parse tree for some sentence. Yeah, that's what it means. Some production has two non-terminals. No. So it's B. Fortran. Ooh, finally, last question. Fortran is it's not a regular language. It also has variables, so it has that declare before use thingy that we were talking about for C. So it is not context free. It is context sensitive. We are done. That was a lot of work. But thankfully, I'm all done with that. Thank you, and I'll see you all next time.